So, hello everyone. It's 11:40 sharp, so let's start the presentation. Do developer dreams of stateless apps? So, some time ago, I got back to the lecture of Do Androids Dream of Electric Sheep by Philip K. Dick, a sci-fi book, sorry. And you may also know this story from the movie with Harrison Ford and Rutger Hauer, the Blade Runner. And in this sci-fi story, in the sci-fi world, so-called Blade Runners are like trained detectives, trained hunters that have to solve issues with the problematic androids. And actually, androids want to live their artificial lives, so they strike back, and they really make Blade Runners' lives hard, troublesome, and not very easy. So I thought that our job as developers is quite similar to those Blade Runners jobs because we also need to solve problems. Okay, we don't have to fight androids until you're not a mobile developer, but still we've got the job to build highly available system, highly performant systems, and there is one guy that can really strike us badly and painfully, and his name is state, as it very often complicates our architecture and our system. So I came up with this question, do we dream of stateless apps? Because then our dreams would be peaceful and we wouldn't get any troubles. My name is Łukasz Gebel, and I'm a software engineer at TomTom. I work at Location and Navigation Services department when we build services that, for example, helps you to dispatch a large fleet of cars in an optimal way so they can reach their destinations in safe and sound manner. So I also have experience in building distributed stateful systems in basically mainly built in Azure Cloud. In the past, I also worked in AWS, and today I would like to share my thoughts and my experiences with you in context of high availability of such systems. So I will focus mainly on Azure. However, I will point some snippets or some equivalents in AWS Cloud also. So I will have three main parts in my presentation. So firstly, I will start with some simple strategies that we can use to make our system highly available. Then I will go to tools that help us to manage state in the cloud systems and their highly available features. And finally, I will try to demystify the acronym SLA, and we will do some math. But first thing first, let's define the state. So usually when we think of state, it's like quite intuitively we know what it is. So it's like a primitive idea, like a set in a mathematical world. So we know that, for example, light switch can be in a state on or off. We can be in different states, so we can be sad, happy, interested, and so on. So the formal definition by Cambridge Dictionary said that state is a condition or a way of being that exists at a particular time. So there are two main things. So it's a way of being and it is tied to a particular point at a time. In computer science, we usually think of a stateful program as a system that is able to remember the preceding events or user interactions. And this remembered information is called the state of the system, the state of the application. So it's like a brain. It keeps all the information and then we can use it to take some actions or solve some problems. So state is actually everywhere in our applications. So we keep state in variables, in databases, in files. However, we don't call every application stateful. So let's look at three different most general architecture, and I will discuss them in context of being stateful or stateless. So the first model, very simple one, is the fully stateless one. And here we've got servers that can handle requests on their own, and clients can send requests which are going through load balancer, and it doesn't really matter which request goes on which server because there is no shared state. So it's quite simple setup. And it's not very problematic because if one server is down, the other can take over its request and our system is still highly available. The second architecture is where we've got some third-party component like a database, and servers are capable of reconstructing needed state using this third-party component. And when I did some research, I found out that some people find this architecture as a stateless. And the argument is that servers on their own doesn't keep a setup, it doesn't keep a state, and they just communicate with this third-party component. So every server can handle requests from clients independently, just being based on this third-party component. However, in my opinion, and also in opinion with other people, it is stateful setup because we still have this third-party component. We have our database, we've got our cache or anything that keeps our state. And without it, our system is useless. It probably cannot work. And we've got the third setup, a fully stateful one. And by this fully stateful, I mean the setup where every server keeps all of the state it's needed for the given client it handles. And here we have also something called sticky load balancer, and it simply routes requests from one client always to the same server. So one server is forever responsible for handling all requests from this particular clients, and it keeps all the state that is needed for this client. However, this stateful is really faulty because if you lost this server or the load from the client is big enough to kill your server, you're in trouble because you don't have any redundant one that could cope with it. So I like to call this one the awfully stateful architecture. However, if you want to use it, I think it's okay until you are very sure that that's what you need, and you need to be simply sure to go that way. So these are these three most general stateful versus stateless apps architectures. So now let's move to the high availability strategies. So in our cloud environments, we can go with simple scaling, and the two main scaling types are vertical and horizontal. By vertical scaling, we mean that we can make our machines more powerful, we can add them more resources like CPUs, RAM, GPUs, anything that we need, and machines can handle more load. Usually, sometimes it means that such a resource needs to be stopped, and then we add the resource, and then it is back again. So on contrary, we've got the horizontal scaling. And in horizontal scaling, we have the same types of machines with the same resources, and we simply add them on the go or decrease its number when the load is decreasing. Then we can go for multi-region deployments. To don't have a single point of failure in one cloud region, we can deploy our applications in many regions. So in cloud environments, usually we have this region that contains at least one data center and availability zones, which are single data centers. So let's look how it looks like in Azure and AWS. So according to Azure documentation, we've got 60 regions. However, if you scroll down, you will see that currently they have 53 regions, and there are 7 regions that are already announced. And they have 10 regions with availability zones. Every region with availability zones have minimum 3 AZs. On contrary, in AWS, we've got only 23 regions. However, they took different strategies, so they provide much more availability zones. So we've got 70 availability zones available in every of this region. And usually we've got 2 or more AZs, except the Osaka region, which is a special one. So when we are placing our resources of our distributed systems, we should think how we want to place them, so how it works under the hood on our cloud. So for example, we can go for availability sets or scale sets inside one region, and then our machines will be close to each other, so we will have minimal latency between them. And if our node needs to communicate, for example, to synchronize some state, the latency low latency is crucial. However, then our availability is lower because they are stacked in the same, for example, fault domains. And fault domain in Azure is simply a simple rack, single rack in a data center. And availability sets and scale sets have different number of available fault domains. So it means that your VMs can be spread over different racks to make it more available. There are also update domains, which means that machines from the given update domain won't be updated at the same time. So it will be like a sequential update. So you've got still some resources up and running. And when you're putting your resources, you have to think about this latency versus availability. So as I said, if you go for availability sets or scale sets, you have minimal latency. But if your racks or the data center or the whole region is down, you're down. So you can go a little bit further for availability and deploy your application on different availability zones. However, then the latency between availability zones is a little bit bigger than latency inside the same data center, but you gain the availability. And finally, you can go for this multi-region deployment. But if you've got a lot of nodes that needs to communicate with each other, and you've got like East US and West US stack, so probably the latency will be too big for you. However, these options are available. In AWS, we've got these VM placement strategies. So we can choose a cluster strategy, then all of our resources will land on a single rack. We've got a partition strategy, so we can create logical partitions, and these logical partitions, we choose which resources goes on which racks. And the spread one, it means that simply our resources will be spread over all fault domains, over all different racks to have higher availability. But why we should even care about such things? So very often in distributed system, stateful ones, we need to coordinate our clusters. And for example, we need to synchronize some state, we need to synchronize configuration of such a cluster, and we could use Zookeepers for this. And Zookeepers works in this manner that they need some kind of quorum, and you need to have 2n plus 1 instances. So minimal highly available setup is 3 instances. When one Zookeeper is down, the 2 others can still cooperate. However, if 2 are down, the Zookeepers cluster with 3 instances is down. So let's say that you want for HA setup, you set up 3 instances of your Zookeepers, but you didn't really check how many fault domains you've got in your region. So it occurs that you've got only 2 fault domains, so 2 racks. So your Zookeepers are spread like this. You've got 2 Zookeepers on one rack and the third one on the second rack. And let's say that some natural disaster happened, and unfortunately the rack with 2 Zookeepers is down. And in such case, even though you had your 3 Zookeepers, you had only 2 fault domains, and your quorum is down because you were unlucky, and the 2 Zookeepers were down. The rack with 2 Zookeepers were down. So maybe let's scale up and put more Zookeepers. We've got 5 Zookeepers now, so 2 of them can be down, and 3 of them will be still working well. But still, if you've got only 2 fault domains, 2 racks, and if you're unlucky, your Zookeepers will be spread like this, and 3 of them may go down, and these 2 are useless. So I would like to highlight that we should be aware how our resources are placed over different regions and in the cloud infrastructure, because sometimes it can really strike back and be quite painful if we're not aware of it. Okay, so let's move to highly available cloud services in context of their availability. So usually when we deal with state, very often we need some kind of database. And we had some experience with Azure SQL. So Azure SQL is simply a managed DB. Under the hood, there is a Microsoft SQL Server database engine, and it has pretty cool scalability and high availability features. So for scalability, it has something called dynamic scaling, but you need to be aware of the fact that it's not equal to auto-scaling. So it's simply a manual process, but you can scale your database on the go. All you get is a toggle in a portal, or you can access it by a REST API and you can scale up or scale down your database on the go. If you'd like to have some more automating kind of scaling, you can go for elastic pools when you set up a pool of resources and your databases share them and use them if they need. Or you can implement your custom auto-scaling based on this Azure SQL metrics, and you can run up and down requests to REST by REST API to the cloud provider, and your database will scale depending on your actions. Regarding high availability features, it has something called active geo-replication and failover groups. So let's start with the active geo-replication. So in active geo-replication, you simply get your primary database in one of the cloud regions, and then you get a secondary database that can be in the same or a different region. Additionally, you get asynchronous data replications between two regions, and you get a toggle that is used to switch your primary database to a secondary database. So if you see that a region is down, you can do this failover. However, it's a manual process and probably it's too slow. So if you want to have a highly available setup, you don't want to have manual processes at all. So we needed something better. And Azure provides something better. It's called failover groups. So here we've got our primary and secondary database as we get before. However, now the secondary database is by default in different regions, so we get higher availability. Data is also asynchronously synchronized. And additionally, we get this nice guy, like a robot, who checks if our region is down, and if so, it is capable of doing automatic failover. So we got a single connection string to our database, to our primary DB. It always points to our current primary DB. If something bad happens, this nice guy will switch it, and our secondary database will become a primary one. What is more, we can benefit from something called paired regions on Azure. So paired regions are simply a list of pairs, and these regions have these guarantees from Microsoft's side. So they provide a physical isolation. So if it's possible, the data centers are at least 300 miles. So the natural disasters shouldn't break two regions at the same time. We've got region recovery order. So if two regions are from a pair are down at the same time, one of them is prioritized to recover. And they also get these sequential updates, so they are not updated at the same time. If the update on one region fails, it is recovered, and we still have the second region working. Okay, so now let me do some demo. I will show you an app. So I prepared a simple Java app, the app Azure SQL. And here I will use the SQL data access object. And it will simply select all Androids from my database or create a new Android. And Android is simply defined by identifier, first name, last name, and its version. So these are simple SQL statements. I use the JDBC template, and in the app, I'll run my scheduled executor, and I will create an Android, and then I will select all Androids and log the size. So let's run it. And here we go. It should start in a moment. And we've got our Androids being created. Now I will switch to Azure Portal. And here is my failover setup. So I have two databases in two regions, in East US and West US, and two servers for each database. And now when I check one of the servers, I will have this failover group features. So we've got this failover tab, and here we see that our primary server is currently a state runner server East US, and secondary server is the West US. We get some nice visualization of our regions that are paired. We get our read light connection string, so that one that points to the primary database all the time. And we also get some secondary read-only listener endpoints, so we can balance our workflows between reads and writes if we need it. One of the cool features with failover groups is that we can simulate a failover. And now I will simulate such a catastrophic event. So yes, I agree that it may not work. And let's see if there is some disruption in our application. So failover should start happening. Oh, we get some errors. And yes, our connection was reset, so primary is not primary anymore. And we've got more errors. Some of our requests failed, but really quickly our database is up and running, so we probably could fix it by applying some retry policies, and we won't be vulnerable for this error. So what are my experiences with using this Azure SQL? So we used this quite a long time ago, like 1 or 2 years ago, and we were really unhappy with it. So as you can see, I was quite sleepy while using Azure SQL because it didn't work so well there then. So basically, such a failovers usually took 5 to 10 minutes before your primary database was accessible again, or secondary became primary one. There were a lot of internal failovers inside one region, so even the failover to the secondary regions didn't start it, and you get some troubles with your database, so it didn't work very well. However, as you could see, now it's fixed and it's a really nice feature. So what is more, they added more features like a business critical tier and the zone redundant deployments, so your app will be even more highly available. If you're interested in Amazon equivalent, you can check the Amazon RDS database. It has many different engines under the hood, like Postgres, MySQL. It also supports different AZs, synchronous replication and standby replicas, and so on. So I would say that's the equivalent of Azure SQL in Amazon RDS. But still, we were very unhappy and we had some problems at this particular moment in time. So we lay down, cry, and looked to the sky, and we discovered Cosmos. And Cosmos DB is also a managed service on Azure Cloud, and it's simply a multimodal DB. It's NoSQL database, and it supports many different APIs. So you can go for all good SQL, the MongoDB, or Gremlin if you like GraphQL. So that's how Cosmos looks like, and that's what it supports. And it has really nice high availability features. So you can go for single master or multiple reduce replications, as well as you can choose a multi-master replication. And you can add and remove regions on the go when your app is already deployed. So you can expand your app all over the world. What is more, you've got something called multi-homing API, and it means that your client will act and will contact the replica that is closest to you, and it also has regional failovers in case of any disasters. Under the hood, when it comes about data replications, so your data partitions are regionally redundant, and every partition is replicated inside one region, and your replicas can have from 10 to 20 fault domains, so the probability that all racks are down is really low. And you've got 4 replicas times the number of regions in which you deployed your Cosmos DB. So now let's do the same setup, but with the Azure Cosmos. So in my Cosmos application, I got my Cosmos data access object, and here we use documents because it's a no SQL database. However, I will use a simple synchronous SQL API. So to create new Android, I simply use the abstraction provided by Azure SDKs. I create a document, and I have to serialize my Android to JSON, and that's how this Android document lands in a Cosmos DB. And to find all documents, I need to query and download all documents from my Cosmos DB. As I said, I use this simple SQL API. The app will be pretty the same as with the SQL one. So I've got the executor, and I create a new Android and then find all Androids available, but now with this Cosmos data access object. So let me run it. And in a moment, we should see our Androids should be created. Yeah, so we get our Androids. So let's move to the Azure portal again. And now I will show you the resource group with my Cosmos DB account. Sorry, yeah, here it is. So here we've got the Cosmos DB account, and we also got the tab called Replicate Data Globally. We get a nice map. So we've got this multi-region rights feature. However, it is disabled because I would like to compare apples to apples. So the SQL version that I showed you didn't have multi-region rights and multi-master rights. And we can get this automatic failover and manual failover to simulate this situation. So now let's run the manual failover. And we need to choose which region should be our right region. So we will switch it to the West Europe. Yes, I understand the risk. And let's switch to the app. And failover now is happening, but our Androids are still being created. We could wait for a moment if we see something dangerous or some errors. However, from my experience, we could wait like for an hour or longer, and you really won't get any issues. So I wasn't able to replicate or get any errors from failovers on Cosmos DB during the test that I run. So this feature works really well, and it was a solution in our case. So still, Cosmos DB has really nice availability, but you need to be aware of its limitations. So document size are at maximum 2 megabytes, and it supports only 5 geospatial functions. So if you need some more sophisticated database functions, you probably need to implement them on their own, as Cosmos DB dataset functions is quite simple. And you need to remember it's document-based DB, so with all its pros and cons. There are also, as usual, a consistency level that you can choose from. You need to be aware of them, and you need to choose the right consistency level for your application. In Amazon, you can check the DynamoDB. I would say it's the equivalent of Cosmos DB. It also has this multi-region and multi-master support, but I haven't used it, so you can check it if you're interested in. Okay, the next group of services is storage. So sometimes we've got some distributed resources, some files that we'd like to share, backups, logs, or in general, long-living resources. So we need some kind of storage for them. And in Azure, we get this locally redundant storage, and it means that your data will be replicated 3 times within a single data center in a region that you choose. If you need to be more sure, you can go for geo-redundant storage, and then you will get the 3 times replication in your primary region, and then the asynchronous replication to the secondary region. However, there is a trick. You won't be able to read your data from the secondary region until your primary region will fail and cloud provider will decide to switch your primary to the secondary one. If you want to read your data from the secondary region, you need to, of course, pay for it, and you can go for read access geo-redundant storage. So now you've got 6 replicas in 2 different regions, and you can access both of them. We can go even deeper if we need more redundancy. In Azure Storage V2, we've got zone redundant storage. So we can make our data redundant between different availability zones. So with zone redundant storage, we've got 3 clusters in different AZs. In the geo zone redundant storage, we've got zone redundant storage plus the secondary region, but still we won't be able to read from the secondary region. And finally, we've got this read access geo zone redundant storage. Oof. So here you've got your data spread over different regions, over different AZs, and you can read from both regions. However, you need to be aware of what you're asking for. So it's like in a story about the gym. So if you want your data to be redundant, it needs some time to be stored and replicated. And if you need your data as quickly as possible, you should probably go with locally redundant storage and don't really care about the redundancy so much. So choose wisely. Then in a pack of storage services in Azure, we've got Azure Queue, which is a really nice and simple service to integrate the parts of your applications or different services. It has infinite time to live and it can store up to 500 terabytes of messages. And of course, order is not guaranteed, but as I said, it's quite simple service, which provides you some kind of persistence over your storing your messages. If you need ordering, you can check out the service bus message service on Azure. Okay, when you check the documentation of Azure Queue, it says it supports unlimited number of concurrent clients. So I was quite suspicious about it. So I started with like, let's do what one client can do with the queue, and let's do some big load with this one client. And suddenly you can get 305 server busy. So I'm usually quite skeptical with such statement that something is unlimited. There are always some limits, and I think that developers are usually quite skeptical about using such statements. However, we do not always write the documentation, and that's the case. In AWS, we've got S3, which is the equivalent of the storage, and SQS, which is a queue for storing our messages. And at the time we used AWS, it had more mature Java SDKs, but still Microsoft do a lot of great work on improving their SDKs, Java SDKs. They are really reacting when you are creating an issues on GitHub, and they are improving very, very fast, and the SDKs are more and more mature, and still they are better. And when you have your storage, it can still fail, as anything in cloud or in a distributed system. So we should think of some kind of storage lifecycle or be ready for migration, because sometimes the storage can be moved to the new types of the machines. So to benefit from new machines, to benefit from the better performance, we would need to migrate our storage accounts, our databases, and so on. So one strategy that we could take is to put a proxy bit for our service and simply direct all requests to the old setup. And after some period, if the old data is not anymore needed, we can push new requests, old requests to the new setup. However, the proxy has some cons. So you add some latency, additional latency, some additional overhead to your system. And from my experience, such proxy component is maintained and developed only when it's needed, and then after some time it gets rusty. So when you want to reuse it, it's not ready for being reused. So maybe the better way is to go with some kind of dynamic approach. So like defining a pool of storage accounts that can be dynamically configurable. And for example, if one of the storage accounts goes down, you can take it out of the pool and don't write requests to it, and provide a new storage accounts to your pool or new queues. So you can dynamically have a healthy and living system. So I think I would go with this way. Okay, so let's go to the first chapter, the SLA, which means Service Level Agreement. And SLA, by definition, is a contractual agreement between a service provider and a customer buying a service. And probably we are usually on both sides of this agreement because we are providing some services, but we also are users, for example, of cloud services. So we are customers of cloud providers. And the SLAs very often stipulate some minimum quality of services. And if it is broken, we need to pay or we get some money from the guy that we signed the agreement with. So how we can understand the SLA? Let me use this SLA calculator, which is written in Lisp, and it's made with secret alien technology. I really like it because it fits my background story about Blade Runner. So here it is. And one way of understanding the SLA is defining it by the number of nines. And it means that our system is up for 99.9% of time. Putting it in a different words, it means that during the year, our system can be down for around 9 hours. And the more nines we get, the better for our availability. I really like this tool because it really supports also artificial intelligence. So I can write the 5 nines and it should understand the natural language. So it's really powerful one. But get back to the SLA. So as I said, the more nines we get, the better. And how can we calculate it for our system? So let's have such a simple setup. Let's assume that we have a system that uses a DB and storage, and we need to use them at the same time to be up, and both services have 4 nines of availability. So what's our SLA in such a setup? So let's use the uptime approach. So that's the part where maths comes to the rescue, and we will use the probability. When two events A and B are independent, the probability of both occurring is simply the probability of event A times the probability of event B. So the probability of database being up is 0.49, and that's the same for our storage. So probability for both storage and database being up is 3 nines. So as you can see, we started with 4 nines for our services. However, after combining only 2 of them, we already lost 1 9. It turns out to be 8 now. And it's like an hour of being up during the year. So how can we improve? So we can go for multi-region. So we can deploy our application in 2 regions and have a traffic manager that routes our traffic between these regions. So in such setup, our traffic manager will have 4 nines of availability. And if our system is up, it means that, let's say, our Europe region is up or our US region is up. Putting it in a different words, maximum probability is 1. So we've got 1 minus the probability that the Europe region and US region at the same time are down. Then the whole system is down. So we simply can multiply the probabilities of these 2 events, Europe being down and US being down. Okay, so let's calculate it. Probability of Europe being down or US being down, they are the same, and they are simply the maximum probability minus the probability of a single region that we calculated before, and it's this value. So putting this into formula, the probability that Europe is up or US is up, so of our multi-region deployment, is 1 minus this multiplication, and finally we've got like 1, 2, 3, 4, 5, 6, 7 nines, which is really high availability, which is really high SLA. That's great. However, we have this traffic manager in front of us. So we still need to multiply this high SLA by the 4 nines. And finally, the SLA of our multi-region is again 3 nines, but we are very close to regaining the 4th nine. So as you could see, it's really easy to lower your SLA. However, it's really hard to get it back. And we doubled cost because we have 2 deployments. So we need to be really careful. And I would really like to highlight it that complexity is decidedly simple. So when we are designing our systems, it's very easy to go with this thinking that, okay, it's very simple to let's get a database, let's get a queue, storage, and maybe some Redis cache, and let's put all over together because it seems to be simple and we just get services that we need. However, when we do it, it may be occur that simple solution ends up with being really hard and complex architecture, and we are ending up with many different problems, and it really harms our availability. So we should be really careful and put a lot of attention to our architecture. Okay, so summarizing, I went through strategies, tools, and this SLA in context of being up or down. Now I've got a call to action for you. So I would like to ask you to do this kind of exercise, mental exercise, to calculate SLA for your system at work or for your hobby project. It doesn't really matter. I think it's a good exercise and it's quite a good metric to get the complexity of your system, the metric of the complexity of your system. Then I encourage you to play with HA features of the services that you use and always be ready for the failures because they will fail. If you never experience the failure of cloud services, I'm sure, unfortunately, you will in the future. So we need to be ready for it. And finally, try to be aware how you are using your cloud infrastructure, where your resources land, because sometimes you may think that you've got the highly available architecture. However, you missed one little thing under the hood, and it turns out that you get outages, and you can prevent it quite easily when you're aware of these things. Okay, so finally answering the question, do we dream of stateless apps? So I think we shouldn't, because state brings a lot of challenges, a lot of problems to solve. However, it makes our work interesting, and he's like a good buddy that challenges us and helps us to develop ourselves and to make our systems better and better. So I think that we shouldn't dream of stateless apps. We should try to take on the challenge and simply solve the problem, and everyone will benefit from it. Okay, summarizing. I hope you enjoyed the talk. I hope you will enjoy the whole conference. Feel free to ask the questions on Stack. In a moment, I will try to answer if there are any. And I started with Roy Batty, the Android from the Blade Runner, who was at the first slides, and I would like to finish with his citation. So I hope this presentation, the whole conference, will be a great experience for you, and it won't lost in the rain. Thank you very much for your attention. Feel free to reach out to me. So now I'd be happy to answer your questions. And here is the bibliography. And I will put the slides and codes under these links. I will also put it on Twitter.